years of diving. Yeah, you can talk to them about that. And he's going down under and looking at amazing things, some of which appear behind us. This is a montage of images that Dale has taken in his dives in truly extraordinary places that take us into another environment where there is extreme life. Darlene Lim explores lakes in Canada that have amazing things growing in the bottoms of them. And she's done a lot of really interesting work, again, on odd and unusual forms of life growing in unusual circumstances. And finally, Pascal Lee, down there at the end of the table, is a person who doesn't much dive on Devon Island because it's pretty dry. It's one of the best analogs for Mars on Earth. And so, like Mars, there's not a lot of lakes lying around. There's a few polar bears. I guess you always have to carry a 30-06 with you, but it's a great place to go and look to understand the geology and the terrain of Mars by going to a place that's quite similar. I'd like to make one more note about Pascal Lee. He's starting a project called Mars on Earth, and he wants to engage the broad public and even the world in understanding how to build and understand, or how to build a program that will help us really understand Mars. He was at the SETI Institute booth this morning at 10:30 talking about this project because he wishes to engage the truly adventuresome in that. So if you think you want to get involved with Pascal and all the great things he does up at the Houghton Meteor Crater, a place where a meteor did hit the Earth, talk to Pascal after this. All of these people are, in my mind, adventure scientists. And so I'd like to turn over the microphone to them and have each of them talk for 5 minutes or so about what motivates them to spend their career and their lives exploring extreme environments for life and what kinds of things that tells us. And then we'll kind of go back around again and you can comment on each other. And after about 30 minutes, we'll open up the floor for questions. Here we go. Natalie.
All right, I think I'm going to start with the basics and just to talk about what do we call extremophiles. And extremophiles is really with respect to us. When we go to places that receive high UV, or in places that you have boiling waters, or it's really cold, or it's really hot, or really acidic, these places are nasty for us, but the microorganisms that live there, I'm not saying that they are happy there, but they thrive in this kind of environment, they reproduce and they stay there, so it might not be so bad for themselves. So we have to keep in mind that extremophile is with respect to us, but the reason, what motivates me is just, look at the budget of NASA right now. It's not tomorrow that I can get a rocket to get me to Mars. So short of being able to go to Mars right now, I have to find places on Earth that look like Mars, or periods of time on Mars that I'm interested in. And that means that early in the history of Mars, when the conditions were more similar to those of Earth right now. And also, when you go to those places, especially in the high Andes, when we're going close to 20,000 feet in elevation, you are going back on time. As you go high on Earth, you are going back in time on Mars, just because the air is getting thinner, the temperature is getting cooler, and because the air is thinner, you have these huge variation in temperature that are pretty much equivalent to what you have on Mars. And because we are climbing volcanoes, we have this volcanic environment that is very similar to Mars. So this is a great place, really. And there is a scientific motivation to understand what was going on Mars at the time. We know that there were lakes on Mars. That was the first thing that motivated me to go and study lakes on Earth, and probably you too, Dale and Darlene, the same thing. But when you get to the point to say, okay, we have the evidence that lakes are there on Mars, then what happened to life? It was there when climate changed on Mars 3.5 billion years ago. How much time? How did it happen? Was there enough time for life to migrate from one environment to the next. It is obvious, unless life is very, very different on Mars than the life we know here on Earth, that surface conditions on Mars are not viable for life as we know it today. So there was a point where either the surface life on Mars completely disappeared and what's left, if there is anything, there is in the subsurface, or maybe some species at the surface had the time to migrate. And by going to those places that we call analogs on Earth, we are learning all of that. We are learning what type of microorganism survive, the type of environment that Mars experienced way back then, and also, even more importantly for us, how to recognize them, how to recognize their signature. So there will be a sign of the activity of this microorganism. They are going to be interacting with their environment. And through their cycles of life and death, they are going to leave chemical and mineralogical signatures that you are learning to recognize. So this is one of the primary motivation for me. The other one is something that came after a few years, but I'm a little slow. So I started with a Mars motivation, really, and going really high on these mountains and looking at this lake changing year after year and trying to figure out, yes, sure, this is a good equivalent to Mars. And after 2 or 3 years, say, yeah, but it's also what's happening right here and right now on our own planet. And so all of a sudden it became more important in my mind that going to explore, to understand other planets also makes us aware a lot, faster of what's going on our own planet. And this is where planetary exploration loops back and helps us look at what is going on here and now and maybe trying to find solutions. At the same time that we are looking for exploration on Mars, we are looking also at maybe finding solution to what was going on and just understand it. And maybe if we don't have the answer, at least learn how to ask the right question about our own environment. So these are 2 scientific motivations. There are others, but there are other panelists here. So, Dale?
That actually kind of sums up my talk as well. I mean, what motivates me is exactly the same thing. We want to go back and take a trip that transcends time and distance. So when I go to the Antarctic or when I go to the high Arctic to look at the lakes that I look at in the Antarctic or the springs that I see in the Arctic, it's literally taken us back in time to look at Earth's earliest biosphere. Matter of fact, here, if you look at the bottom of the screen, right down in here, what we did was we went into a lake in the mountains of Queen Maud Land. So if you went straight south of Africa and hit the Antarctic continent and then took a skidoo, which is what we do, and skidoo in about 120 kilometers or so into the mountains, set up a camp for a couple of months, make a hole through the ice of the lake, which is thicker than this ice, or the room is thick. When we dove down into these lakes, it really was like a time tunnel. And this is one of the few places on the planet where you can go and these microbial communities exist, and they're growing in ways that they did 3.5 billion years ago. And so that's the lesson that we take from there is when we had life on this planet and it was really working quite well, we know that there was liquid water on the surface of Mars. And Mars may have always been cold. It may never have been much warmer than the McMurdo Dry Valleys or other places that we look at in the Arctic or the Antarctic. And so similar environments may have been ice covered like this. So if we can understand what's going on in these lakes here on Earth, it helps us interpret the fossil record that we see, for example, in Australia. Actually, can you just shoot one more slide? Or actually one more. So what I want to show you here is actually a comparison. So on the left-hand side of the screen in the top, you can actually see some samples of rocks that I looked at in Australia last summer. And these are from the Pilbara region in Western Australia, the Australia Pool Formation. And this is 3.5 billion year old evidence of life on our planet. And they're forming these cones. And you can even see in this bottom layer here, there actually is a 3-dimensional cone that was silicified in the rock record. And if you compare it to the cone that's over on the right in the previous image, you see that they're extremely similar. And as far as we know, Lake Untersee in Queen Maud Land is the only location on the planet that we have these large conical stromatolites that are forming like this. We don't know why. It's a puzzle. And it's going to keep us occupied for probably a few more years to even come close to understanding that. But it's a very, very different environment, and one that I just thoroughly love to play in, that's for sure, because it is a journey. You know, we have a small group of people that go out there. We have to work for 2 months together, usually 6 people. Could you go back one slide for me? And it's a very severe environment just for us as well. So it's an extreme environment in 2 ways. It's an extreme environment for the organisms that can make a living there. Once they get there and they habituate the place they're at, they're okay. But they have to get there. And like our trip, it's a very difficult one, and we can experience really hard times on the surface. You know, it's an extremely windy place. As you can see in the upper shot there, that was one of our not-so-bad storms. Sometimes we hit winds of 110 miles an hour while we're at the camp. Sometimes our tents explode. But that's the kind of thing that we just have to deal with once we're there. So that's what attracts me to this work. So the thing that compels me to do this work is 2 things, really. It's asking the questions, the scientific questions that we're interested in, and trying to look for those answers. But there's another toolbox that I've got to go to, another whole set of experiences that I've got to make to make this happen. So I have to educate myself how to go into these environments and learn to work there. So it's like getting a separate education. And I've been doing this off and on now for 34 years. I've probably got about 6 or 7 years in a tent in the Antarctic and various places, or the Arctic. I've circumnavigated half the continent by icebreaker. In fact, I met my wife on a Soviet icebreaker. And you end up making friendships that last for years and years and years. I'm working with some of the same Russians on this project right now that I've worked with 20 years ago. So there's lots of elements to this that make the story compelling and keeps me involved. And that's just what I want to do. I just want to keep working like this and keep asking those questions and looking for the answers.
Okay. Let me just scroll through here. There you go. Ditto, completely ditto, in that I feel very fortunate when I wake up in the morning because I get to do exactly what I want to do. And I'm happiest by the water as well, especially lakes. My last name happens to be Lim, and so limnology is the study of freshwater systems. It was just like too easy. But I have been working in what a lot of people consider hostile or extreme environments in different deserts, cold deserts up in the Arctic. That's where I met many of the people here. And also in underwater environments, which is where I do a lot of my field work. But actually, my scientific interest is actually looking at organisms doing seemingly extreme things, building biominerals, and constructing very large-scale items in what are generally, for all intents and purposes, we can describe as non-extreme environments. But I think my role here on this panel is to also speak greatly to what Dale was speaking to, which is the fact that my interest, in going into these field settings has actually grown and evolved, and I'm able to tap into my, love of human exploration. And so, for me, sitting on this panel, looking at life in extreme environments, I think what I'd love to speak to you about just for a few minutes is just putting human life into extreme environments and the preparations required to actually do that in a way which enables us to efficiently conduct our science. And this, for many field scientists, those that are sitting here, everybody's been doing fieldwork for years. There's so much planning that goes into a trip, even if it's for 10 days, especially into the environments that we go into. And we do that, it's kind of second nature. You're trained to do that as a monkey when you're an undergraduate assistant, and you just kind of learn and learn and learn, and there's so much involved in it. But what I'm interested in is beyond that as well, is what else can we concern ourselves with, and what else do we need to concern ourselves with to enable us to do science on other planets in a way which is efficient, which is productive, and most importantly, 2 things, safe and also protective of the environment in which we're studying. Because it's useless, as I brought up last night, who was there, for anyone that was there, if the scientists are not safe, if they die, then they're not really useful. And the other thing is, we want to actually protect and preserve the environment in which we're studying. So one of the projects that I've been working on is actually in 2 Canadian lakes up in Canada that harbor these large-scale rocks that you see in the bottom called microbialites. They're built, the rocks built by some sort of microbial interaction with their environment. But the work that we do from the surface, we do with divers. Dale has dove with us many times. He's an amazing, amazing diver. And we were very fortunate to get some funding to put single-person submersibles in this lake setting as well. We used the subs that you see in the middle panel there to actually map these lakes extensively. They're deep lakes, are also quite large. The largest one we deal with is 6 kilometers in length. And so for the mapping that we wanted to do, we had to go through a series of decision-making points to figure out what was the best tool that we could use to actually accomplish the scientific goals that we had. Now, as a consequence of that, we realized that very seamlessly we have this perfect analog, as Natalie was speaking about earlier, to any hostile environment you could imagine, particularly space. And since we're at SETI, and I sit at NASA actually, at NASA Ames, I mean, it just kind of made sense. It would have been ridiculous to kind of pass up this opportunity. So we use autonomous underwater vehicles, which is the torpedo-like thing that you see up in the top there with the diver. And we use that to collect long-range remote sensing data, which we use as sort of an analogy in terms of mission planning when it comes to accessing remote data from different planetary systems with orbiting systems with satellites. We also have divers. That's actually a photograph of Dale, which I found out Dale doesn't actually like, but I think is beautiful. And that's actually, the other astronaut that you see there is actually one of the participants that has been with our program with the Pavilion Lake Research Project for years. And that's him out on an EVA and an extravehicular activity, and very similar in terms of many of the constraints, the limited life support that you're dealing with, and all of the tasks that you have to do while also trying to stay alive. I mean, it's that whole rub your tummy and pat your head thing, but in orders of magnitude, like tricked out. And then at the bottom, you have the beautiful single-person submersibles, which are incredible to fly, which enable us to sit in a very comfortable one-atmosphere environment and do our work underwater, in our case 200 feet down, with cookies and our water beside us. And suddenly, you go from Dale, who's when he's down at like 100 feet and the lakes are up at 2,800 feet, to avoid going into decompression diving, he can only be down there for about 40, 45 minutes. He breathes really slow, so he really extends that. But for people like me who are like, oh my God, this is trying, I'm not down there as long. So I have to be very focused and very pointed in what I do. But if I'm on land, the beauty of doing field research on land is you can look around. You get context to the outcrop, for example, that you're trying to characterize. Very difficult to do when you're in an underwater setting. So these deep workers enable us to actually sit there and take a look around and cogitate on the environment in which we're studying. Much the same way as you see that's called a space exploration vehicle on the bottom section there that's roving around in Arizona. And so that's a pressurized environment which has since evolved into something which, the folks at Johnson, Mike Gernhardt, the astronaut you see there on EVA, is actually the PI of that program, is hoping to kind of fly into things like near-Earth objects and conduct science from that platform. So we formed a very nice partnership with our program, with folks at Johnson, with communications engineers at the Kennedy Space Center who are interested in looking at the way that we communicate with each other. They've forced us to simulate 50-second delays, which is fantastically interesting. And all of this is seamlessly integrated into our program. And so the reason we're doing this, as I mentioned, is to make us as efficient as possible at conducting science in other environments, and to develop the tools and the infrastructure necessary to conduct that research, and not to just design the tools and force fit that to the situation. So I want to just end with a quick anecdote of this story. And when I showed Dale this chart, he's like, what the hell is that? Which is the perfect, proper reaction, because what happened is we had mission operators from NASA Johnson come up, and one of them called me up and she said, we really want to embed ourselves in your program because we're at the end of shuttle and we're moving into solely supporting ISS, International Space Station operations, but we need to grow. We need to learn how to be mission planners in a different environment, and we know that eventually we'll be doing science and that kind of, science operations on other environments, so can we join you? So I was like, totally, sounds good, she's funded, awesome. And so she spent an intensive 3-day period with us, with her team at NASA Ames. All the scientists came in, we met. She asked us, she really drilled down on us in terms of what are the essentials that we need to plan out. We told them, they went away, and in 36 hours they came back with this, and they're like, look, we've planned out your entire field season. And we're like, great, but we don't get it. And we can't use it. And they said, oh. And And they said, well, what do you want? And I was like, look, I got people, especially my program manager, who's out in a million different places at once. And what he needs is a way to just look at his phone and just know where people are, what's going on. If a flight is running late, what does that do to our evening meeting? What does it do to food? What does it do to the science backroom team? So they went away and they made this, which is they took that Gantt chart and simplified it into this beautiful design. And this was the beta version. It's much prettier now. It was called Score Mobile, and now it's called Playbook. And they turned it into a system, an interface which is web-based that we could actually use when we were on site, when we actually had the whole field lit up with Wi-Fi. This has since been turned into an opportunity for other analogs. They're using this now with a program called Resolve, which is an in-situ resource utilization program in a project in Hawaii. They're also looking at commercial applications of this, and so I feel a real joy that we were able to give them a real situation to develop a tool which was truly, really helpful to us. And this is the best analog or a wonderful anecdote that I can share with you in terms of the stuff that we're trying to do with the real science. So looking at the bacteria and look at the humans and seeing how everybody gets along.
Thank you.
Thanks. Sorry that went on a while.
Pascal.
That's great. Yeah, sure. Thanks. Hi, everybody. I'm first of all going to tell you a story about little bugs, cyanobacteria. When the Viking landers, Viking 1 and Viking 2 landed on Mars in the 1970s, 1976 and 77. A cartoon came out following the landing and following the first pictures of the landscape, which showed just rocks. The cartoon showed the Viking landers sitting in a field of rocks. And the caption at the bottom read, "Don't move, they might think we're just rocks." Okay, and the message here is that in extreme environments, life can actually be hidden. Okay, in the same time frame, the mid-70s, a good scientist called Imre Friedman that Dale Anderson knows and has worked with, made a really fascinating discovery in Antarctica. He was in the dry valleys, one of the most driest corners on the planet Earth, and he would pick up sandstones. These are stones that are made of ancient sand that is now essentially cemented into a rock. And if you can imagine that, the grains of sand are actually translucent, so they allow sunlight to come through into the rock. And these sandstones were home, were offering shelters to cyanobacteria. So these are tiny little microbes that are essentially mini plants. They photosynthesize. And they're not at the very surface of the rock where they would be too exposed to the elements, but they are hiding in the nooks and crannies of the rock. Not too far in either, because if they were too deep into the rock, they would be cut off of the sunlight. A bit like caveman or cavewoman, they were in this dusky portion of your cave where you have a bit of light from the outside, a bit of the warmth, but still were sheltered from the environment. So in the top millimeter or so of these sandstones, cyanobacteria were colonizing the rock, so that if you slice this rock open, you would see this rind of green that would be right beneath the surface of the rock. Okay. Sandstones, unfortunately, are not common rocks in the early history of the Earth. Okay. In fact, the rocks that you find early in the history of any planet are likely to be granites and gneisses. Okay. Well, granites and gneisses are very different from sandstones. They're very compact. In fact, that's why you use granite as a kitchen countertop. Okay, it's because they don't have a lot of pores. If you pour something onto granite, it won't just seep through your granite slab. Okay, so granites and gneisses are notorious for being very compact rocks. They are nowhere on Earth, usually, host to any cyanobacteria. Okay, they don't have the porosity, and they also have mineral grains that are too dark to let sunlight through. One of our most interesting and intriguing discoveries at Houghton Crater was the fact that this impact that created a hole 20 kilometers across 21 million years ago went so deep into the Earth's crust, that it excavated rocks that were granites and gneisses from the basement of Devon Island. Okay, so rocks that were about a mile deep were brought up to the surface and were completely shattered, if you will, by the impact shock wave that went through the rock. To the point that some of the minerals that were in the original granite and gneisses got vaporized. And in their stead, in the exact location of these vaporized minerals, there's now a little cave. okay, inside the rock. So the rock itself is quite porous. It's become a sponge, if you will, as rock goes. Well, the point here, the punchline, is that we made this incredible finding, which was all of these shocked gneisses and granites from Houghton Crater are completely colonized by cyanobacteria. Okay. The vaporization of these dark minerals has all of a sudden allowed light to come through. The disappearance of these minerals has created apartment complexes, if you will, for cyanobacteria to lodge themselves in. And we have this really intriguing thing, which is as much as the impacts have been bad news for evolved life, like dinosaurs or things that are really not very adaptable, impacts in the case of Houghton have been a boon for microbes. And this brings us back to the early Earth, when the Earth was made mostly of granites and gneisses. It could well be that impacts were actually a key factor in creating microbial habitats at the surface of the Earth. They would allow microbes to be sheltered from the UV, have plenty of places to colonize the rocks, and therefore grow when the Earth did not have sandstones yet. So I point this out as an example of the type of really interesting, if not insightful, discovery that we are able to make in environments like this. And Dale was alluding to this, I think Natalie as well. We're learning about the Earth and the early history of the Earth in this process of trying to understand life on Mars and where we might find it. So I would not give up completely on even interpreting the Martian landscape today. All these fields of rocks that you see might actually have a cyanobacteria signature, but not visible at the surface. You'd have to crack the rocks open and dig deeper down to find them. Maybe.
Thank you. My boss, Tom Pearson, who deeply regrets not being here, he's in the hospital right now recovering from surgery, calls these guys the Indiana Jones of the SETI Institute, because they are explorers, and they've told you all kinds of serious reasons why they're explorers, but I think that each of them has a deep passion for being out there in the natural world and making unique discoveries. You know, the conical things on the bottom, I can't remember the name at this time of day. Stromatolites, I believe. The conical stromatolites, the constructions that you have found in the lakes, and the little microbes that mend themselves at the tops of volcanoes, and up at Houghton Meteor Crater, what an amazing place. The only thing he ever has to really worry about that he didn't talk about is polar bears. They are the permanent residents. Human beings aren't at that place. So what I'd like to do, we have about, do any of you want to make any comments on each other's presentations, or shall we throw open the floor to questions? Let's throw the floor open to questions, and we have a nice young lady here, Catherine, who will bring you a microphone. Please put it close to your mouth.
Question to Pascal. For the cyanobacteria that you discovered there, is there an implication that they originated there, or did they get there from somewhere else?
Oh, they don't originate there, we don't think. That's a good question. The cyanobacteria colonize habitats, and so in this case, the rock is being colonized and invaded by them. In fact, we've conducted some experiments where we have set up some cozy traps, if you will, for them. In other words, rock samples that are synthetic as well, but some are natural, like salts, where we would just expose them to the Arctic environment, let them soak up the fluids that are circulating there at snow melt. And sure enough, after a couple of seasons, they are colonized by cyanobacteria, who are in the nooks and crannies of the salt crystals. So it's not only is it a dynamic biological system, but it happens quite rapidly, okay, on a time scale of a season or two. So colonization happens quickly. We don't know how long they survive, though. We don't know how long they've been in the rock. We don't know how, that's a much harder thing to measure.
Ashley, can I throw something in on that? So the indoliths that you find in McMurdo Dry Valleys, when Emery was looking at them, it's actually a community. It's not just the cyanobacteria. It's a lichen as well. So you've got fungi and you've got heterotrophic bacteria in there. But one of the comments that Emery said was that these are probably some of the oldest communities on the planet. I mean, these things have been there for tens of thousands of years. So they're growing on geologic timescales and colonizing these rocks. And the other point that Emery always made about these communities, at least the Antarctic ones, is in terms of an extreme environment, like Natalie was saying, most of the environments that we're looking at, the organisms are really highly adapted to these environments. They like it there. You know, it's just that everybody else doesn't like it there, so they're by themselves. The endoliths, on the other hand, are right on the verge of death. They are inside the stones, as Pascal said, but this is a frozen desert down there. And so the key for their survival is actually water. And water is only available for a few days out of the year. And if they don't get that water, they're toast. So their growth optimum is much warmer temperatures. You know, instead of the minus 20 that you get down there, it's closer to 15 degrees C. So if a little snow melt doesn't come in and trickle down through the pores, they're gone. And then all you're left with is large expanses of dead colonies. And that was the other aspect that Emery was looking at these large landscapes of microorganisms which the geologist had walked over for years and years and years. Nobody knew that this was the best place to get a pet rock. He noticed that there was living colonies, and then there was lots of areas that had a very slight climatic change. The snow melt came in too late, or at the wrong periods of time, so when it came down, it just stayed as a mineral form as ice, and those guys just went away. But they do last for long times.
Yep.
Next question.
What improvements in robotic subs would you need so that you could just drop a little sub into one of these lakes and control that from a more comfortable place instead of have to dive in there yourself?
Well, I'll start it, and then I'll let Darlene say something. So
You
we
want to
actually-
take away the fun, huh?
Well, it does. Actually, it comes down to sort of a panel issue tomorrow about humans versus robotic exploration, and I've done it both ways. You know, I took the first remotely operated vehicle that was used in Antarctica to explore these lakes in 1986. In fact, Steve Squires, who's operating the Mare rovers right now, that was actually the very first robotic device he ever used. And we had the opportunity to be using both robotic devices and then going into the water and doing that same work with our hands. And we found, and I think Steve will say this as well, and most people that do this work, there's a place for both of them. So I can go down to 40 meters in these environments. We usually dive pretty conservatively because we're in extremely remote locations, and if we have problems, it's just too bad. You know, we're several days to maybe a couple of weeks before we could get out, depending on what the weather is and everything. But I can go down for 40 minutes at the most, to an hour, hour and a half at the very most if we're really shallow. But then your hands get cold and you got to come out. And I'm on a line, because we're under the ice. So the only way we can get back to the hole, and it actually, if you look up at the lights in the ceiling, off in the distance, a lot of times that's what the hole looks like. A little tiny, go for the light. And we're on lines. Typically in the lakes, we're always on lines. We have communications, and we have to use those lines to get back. So in addition to a time limitation, now we're on a tether. And we got to drag this tether around wherever we go. And it's like being a fish plate, so it does take the effort out of it. And it limits how far I can go out. I can usually go out, usually it's 200 feet. Every once in a while, we'll throw on a 300-foot line if we're really interested in going someplace. But you have to keep in mind, if you go out 300 feet and your regulator shuts off because it freezes up, can you swim a football field on one breath? And usually the answer is no. So that's the risk that we put into that. But with the ROV, or with the manned submersible, we can do that. Now, the remote locations I go to, we couldn't put a manned submersible into them. It's just too difficult. We've got to go through huge amounts of ice, and it's just not practical. Even getting the stuff out there would be hard. But with an ROV or an AUV, we can put those in crates, basically, that are pretty portable and bring them out, and then we just have to have a generator. And then we can operate those all day long. From the surface inside of a warm tent, and we can go out several hundred meters easily and down to the depths of the lake. And that's actually what we do. We use drop cameras and ROVs to get down to the lake I'm working in right now is 170 meters deep at its deep end. The other basin's 100 meters. So the only way we can actually look at that is with cameras. And it's really fun.
Yeah, next question.
Is there any research being done on extreme environments where you don't have the extreme animal life on Earth? One thing that comes to mind is where you may not have water as a solvent for the waste of life, or maybe nothing. Like the kind of things that comes to mind.
I can look for an alley.
Well, I was going to say that, or even in salt domes in the Gulf of Mexico, places where you have natural oil seepages and things like
Right.
that. I mean, fundamentally, all of our life is exactly what we've got. You know, we're all commonly the same life. You know, so there's no different life here on Earth. We're all the same life. It's just a matter of who's exploited it, and if there's an energy source for life to use, they'll take advantage of it. But I can't think of something that's the equivalent of like a lake on Titan, for example.
Yep. Your question brings to mind, however, this example. For example, there's a microbe called Deinococcus radiodurans. It's a weird bug. The name implies that it endures radiation, radiodurans. Okay, and it's a microbe that has, unlike all of us who have normal cells, it has 4 sets of DNA that are identical. And the whole idea is that it can survive in a high radiation environment for which there are no analogs on the Earth. I mean, there's no particular environment on the Earth naturally that we know where such a feature would be required. Okay, and nevertheless, it's able to sustain a relatively high radiation, and because it has these 4 sets of DNA. So if one set is damaged, the others kick in, and that 4th set that's damaged is ignored while it gets repaired, based on the model of the other 4. So it's an incredible example of a life form that is an extremophile, because it could live in a high radiation environment for which there's no analog on the Earth that we could go study, not on the Earth.
So where does it live?
Deserts.
Lives in deserts?
Actually, yeah, the radiation part is a result of its adaptation to a dry environment.
Is this the same little bug that lives in nuclear power plants?
Yes. There's a lot of speculation as to how it acquired its adaptation, of course. So Dale's right. One of them is the fact that it's from evolution from desiccation, from drying up. Yeah, but it's fascinating.
Another question?
Sherry Van Mayer. First of all, I'd like to tell you what happened in the last 30-minute break. We had 3 teenagers, young, giddy, magpie teenagers, going out the front door. Da-da-da-da-da. And one of them was jumping up and down, and they all had on their city name tags. You have a lot to be proud of, if nothing else for that. You've gotten them enthused about the space and what could be out there. Thank you.
Thank you.
Thank you.
I've been following for the last several years the news around Lake Vostok and Antarctica, and it's looks like it could be an analog for Europa or Enceladus or other places in the solar system. But I was just wondering if anybody has some ideas about what might be found in the underground lake, and also what types of processes could sustain life in that kind of environment.
You're the Iceman.
Yeah, okay. Well, actually, I did work on a paper a few years ago that dealt with Lake Vostok. That was a result of some of the work that we've done in the Dry Valley lakes and elsewhere. And so basically, Lake Vostok is a lake that's underneath the continental ice. So it's got 4 kilometers of ice on top of it. And it's liquid because of the latent heat of fusion that's pushed back into the water as ice freezes up. So it's always freezing up at the ice-water interface, and it's always melting a little bit. And so that collection of heat can't diffuse out very fast, and it stays liquid. So that kind of explains that. One of the interesting phenomena that takes place when water freezes up is as you get as you get snow that falls onto the continent, it traps gas in it. So when it turns to firn, to ice, it forms little bubbles in it. And eventually those bubbles will, because there is this cyclic nature, this lake is not completely cut off. It's actually on time scales of about 1 million years, it's always turning over the ice above it. And so there's a convection of this ice going down and some of it leaving. And so all the stuff that was on the top, eventually about a million years, a half a million years, is going to end up in that lake. And that includes the dissolved gases, or the gases that are trapped in that ice. And it pumps, it's just like a bicycle pump pumping up this lake. So one of the effects is that you're going to have all the air group gases that are going to be supersaturated. That means that your nitrogen levels are going to be very high, argon levels are going to be high, and most importantly here is oxygen levels are going to be very high. And so one of the things that you do when you're sick, if you've got trauma and it's infected, you go to a hyperbaric chamber and you go to oxygen therapy, and it kills that bacteria. So our prediction is that the oxygen levels in this lake are going to be extremely high in the water column. Matter of fact, we've modeled that you've got the formation of clathrates, methane clathrates and other clathrates on the bottom. But in the water column, you're actually going to have around 500 milligrams per liter of oxygen in the water. I mean, it's just huge, huge amounts. And I think that's going to keep the microbial action in the water column to a pretty minimal place. They have actually looked at some of the accretionary ice, some of the ice that has formed from the lake water and stuck up onto the ice above, and then it's carried out. So they've drilled down to that before and looked at it, and it was very sparse. Matter of fact, there was arguments as to whether or not they actually found bacteria that was from the lake or if it was contaminants coming in. So I think it's going to be boring in the water column. I think the action is going to be down in the sediments, and and of course there's no light that gets down to this lake. You know, you get below about 20 meters in clear ice, and the lights are out. So this has got 4 kilometers, the lights are definitely out. So it's going to be all based on chemosynthesis. And if there's vents down there, that's sort of a different story, but there's no evidence right now that there's hydrothermal vents of any sort. That'd be kind of cool if it was. But I think once you get into the sediments and you start getting this exchange of electrons, up the electron ladder, I think there'll be a lot of things going on in the sediments. So that's going to be where the fun's going to be.
So another question.
When you look at Mars, for example, you're looking for analogs of extremophiles that exist on Earth that could exist on Mars. The thing that comes to my mind is low pressure. Are there any extremophiles that are adapted to low pressure environments that you're investigating?
We'll get the high altitude lady on that one.
Yeah, but even so, even going at the kind of altitude we are going, which is 20,000 feet, you still have 480 millibar. And that's very, very far from the 6 millibar you have on Mars. I don't know about the pressure. I think that experiments in the space station, for instance, would be closer, something closer to space might be more relevant to that. The kind of analogy we are looking at the high lakes is really the UV part of the extreme. There, yes. You know that we call a high UV index here at sea level when the UV index is 11. When we are up there, it's between 24 and 29. So this is what I start to think in terms of really extreme UV environment. And UVB is really in the short wavelengths. We are getting really close to things that are under 292 nanometers. So we are really getting close to what could have been Mars at the very beginning. As far as pressure is concerned, this is not a good analog. And I don't think that unless you are taking something and you're bringing it to much higher in the atmosphere of Earth, you are not going to get any good analogy.
I think ISS, sorry. I'd have to agree with Natalie that certainly, that's actually one great utility about the ISS, and there are other opportunities coming up in terms of CubeSat launches and then commercial basis as well. I think those are the platforms in which one would want to engage and answer those kinds of questions, because it's going to offer you not only the environment of space, but in particular the access to the radiation effects as well, which is something which is very important in terms of understanding the possibility for life on planets like Mars. So.
I just wanted to add that there actually have been a wide range and series of experiments done for microbial life in low pressure. And it turns out that microbes, generally speaking, are actually quite comfortable with very low pressures. The thing is, the issue really is the fact that at very low pressures, liquid water is now not available in a very wide range of temperatures. And so unless you are in this realm where liquid water is still possible, you are essentially killing life off, not so much because of the pressure itself, but because of the absence of liquid water.
And to continue on that, Pascal, there are places on Mars we know of, and the models show them, and now the imagery shows that we know on Mars you will have a liquid of some sort, might be brines, might be water, but something is flowing at the surface of Mars and can today, even today.
Yes.
My question is about the mutation rate and sort of the length of the life cycle of some of the extremophiles, in case you wanted to sort of engineer them to adapt to the environment like Mars, and something like that would be possible.
Just very quickly, Emery used to say that Crooceriopsis, the main alga that you would find in the endoliths of the dry valleys, would be just happy if you put it out onto the surface of Mars more or less today and brought the temperature and pressure up just a wee bit. So again, as Pascal said, the key here is you have to have organisms that can retain water and then make it through any other deleterious things like cosmic or UV or other forces of radiation. But I don't know, you got anything else you want to say on that?
No, I think so. Sums it up. I mean,
Yes, Monsieur Franck.
Yes, I'm literally in a dream to ask you this question. So, after the four of you here.
We're in trouble.
SpaceX may offer a trip to Mars in 15 years, 20 years. Are you going? And if yes, are you?
I'll keep training. 20 years from now, I hope I'll still be in good shape. But yeah, there is no question in my mind. If I got the opportunity to go, I'll go. Well, first, I like to have ground truth. I do that all the time when I do science. So, I've been, writing hypotheses and writing papers and things like that. And if I have a chance to go see how many things were stupid and were wrong, and, it's better that I figure out myself before being embarrassed. But no, more seriously, I think that all of us here, I am not going to say that we are doing what we do as a surrogate to being on Mars. But I would say that we are all driven by the same passion of exploration. And we are all driven by this incredible desire of understanding what's around us, what the solar system is made of, what the universe is made of. And also, we are very conscious that we are part of a species that need to step off this planet at some point or another, and sooner rather than later. And the best stepping stone for us is literally Mars. It's the closest to home. So if you tell me you have a chance to do that, oh, of course, yes, I would do that. And if you tell me it's a one-way ticket, I don't mind.
I guess I would go in a heartbeat, but I'd have a hard time explaining it to my wife. But I've probably got I'm the old guy here on the stage. I'm 56, so 15 years from now, I'm hoping that I'm going to see people on Mars. And I've been waiting for this for the last 30 years. I'm a product of the Mercury, Apollo, and Gemini programs, and I'm mad that we're not there now. We should have been there 20 years ago. But yeah, I would go in a heartbeat if I could. In the meantime, I've got at least another 10, 12 years, 15 years of work down south and up north.
I would go too, so long as I could come back. I'm not a one-way kind of gal. So.
You wouldn't be alone, we'd be there.
Well, yeah, that's right. No, totally. And that's a discussion that comes up a lot. There is actually there's a big push out of Europe right now that to kind of generating all this energy around going one way and having it all staged. That's truly immigration. But I would go, like I said, if I could come back. And if I went, number one thing is I would love to spend a lot of time making sure that I trained up to be a wonderful observational field scientist for those people that have spent years upon years looking at remote sensing data, being able to know, I would kick over every single rock I could get my hands on for the very reason that, that Dale was speaking about, because you never know, and Pascal too, you never know what's underneath, you never know what's within them. But there are so many other things too that I think if you were to put this question out to the broader planetary sciences community, they would have a bevy of things they would want me to do first, and that's what I would certainly spend a lot of time training to make sure I did. But I'm hopeful that within my lifetime we'll certainly see somebody, hopefully
Or at least sample return.
Yeah, at least sample return. But yeah, let's go. Let's
Pascal,
do it.
how
I'm
about
bored
you?
waiting.
I'm actually curious to know who would in this room go on a round trip to Mars? Okay, on a one-way trip to Mars.
Still a lot of people.
Who thinks it's a crazy idea, really doesn't want to go? Okay. All right, so you are not a representative sampling of the population. We are all extremophiles here, and I want to so of course I would be interested in going, and I want to point out that before we get to Mars, as much as I'm driven, like my friends here, to see humans walk on Mars and go there ourselves, I really think that for a government effort such as NASA's and for other countries, okay, we really need to make this a very realistic program. Okay, it's thinking that somehow it could happen by executive decision one day, like we had the moon landings. Okay, is really gambling that somehow we will have a great enemy again in our near future in history to really have a challenge to beat them at it. Okay. In peacetime, going to Mars is going to be a methodical, step-by-step process. Okay, that's not to say that a private mission could not achieve that goal much faster. Okay, Elon Musk, for example, believes we can put a human on Mars within the next 12 to 15 years. I believe it, and I'm all in favor of it. But for a government agency like NASA, I believe in a stepwise approach to getting to Mars. And one of the key steps is to get humans to Mars orbit. Okay, getting to Mars orbit is a lot easier than getting humans to the surface of Mars. Not only easier, a lot cheaper than to get humans to the surface of Mars. You don't need the big landers, you don't need the greenhouse, the spacesuits that are adapted for Martian gravity. You don't need all of the supplies at the surface of Mars. It's deep in the gravitational well, Mars. It's expensive to get to and get out of. Mars orbit is much more affordable to get to. And I think if we focus our near-term goal or midterm goal to getting humans to Mars orbit, that will get the ball rolling. And of course, once we're in Mars orbit, having the next steps is reaching the Martian surface will be very rapid. So what's in Mars orbit that's really interesting? And well, those are the moons of Mars, Phobos and Deimos. And we would not be going to Mars all the way to Mars just to explore those moons, but they would be a stepping stone in our quest to get to the surface of Mars itself. And so I'm particularly excited by this prospect of getting humans to Mars orbit as our near-term or mid-term goal here, and I really believe in needing to do this. Who would go to Mars on a 3.5-year journey just to go to Mars orbit and not land in this room? Okay, welcome.
That's great.
Right.
I'll preempt the last question, something that I've always loved asking scientists, and I don't think I've ever asked these for this question, is sort of the one-sentence answer to what was it when you were a child set you on the path to become a scientist? For me, my interest in astronomy came out of watching a Perseid meteor shower from an extraordinarily dark place when it was a storm of meteors I couldn't even count. How about you, Natalie?
You have to ask my mom because I don't know. She told me this is the first thing I said.
I'll ask her the next time I see her.
Yeah, I don't have a single eureka moment. I mean, I grew into it. My dad was a Navy diver. He took bombs apart. He was always going off on trips like that to remote places and doing cool work, and I just kind of taken a different path. And science came along, and Cousteau was there to show us the great pictures of everything.
Yeah. My parents were immigrants to Canada, and they had to work all the time, and so I was a latchkey kid, so I watched a lot of TV. But luckily, we had Jacques Cousteau, and I didn't have a eureka moment either, but he was very instrumental in my life. And my parents also really wanted to embrace this new nation, this new continent, and so they took us camping all the time. And that was definitely very instrumental in me wanting to be outside and fell in love with the environment. And then really, like when I was growing up, when people would say, "Oh, what do you want to be when you grow up?" I would just say an explorer, but I didn't really know what that meant. But I didn't really want to be anything else, so I feel very fortunate to be in this company here.
To me, that would be Carl Sagan. Before the Cosmos days, actually, he wrote a fantastic book called The Cosmic Connection, which I think you should read if you can. It actually has a chapter on Phobos and Deimos, incidentally. Carl Sagan was just a real inspiration. I read his book, I think, when I was in my early teens. I was interested in science and space before that, but to become a scientist in planetary science, that was him. And I was lucky enough to be his last TA at Cornell.
So take those stories home to your kids and your grandkids and share them. I'd like to thank our panelists. It's been a great panel. And then